So welcome, everybody. What Gail and I would like to touch on with you tonight in this webinar is to really try to bring the Common Core State Standards mathematical practices to life by looking at some actual problems, and especially problems that technology, we think, has a really pivotal and important role to play in bringing those mathematical practices to light. As you can see on the agenda here, it's really organized around some titles of some problems and scenarios that we'll use as illustrative examples. Pentagon problem is based on actually an assessment item from NAEP. Filling the urn is kind of a dynamic version of a popular kind of reasoning and sense-making task that's found across curricula from lots of different countries. From expressions to equations looks at a really kind of critically but subtle distinction and tries to make that more clear to students. The mass problem is a problem that's many of you will, the context may be a little bit different, but a lot of you will recognize it as kind of a classic problem that we'll be able to see multiple roles of the technology at play. And then confidence levels for proportions looks at really a very difficult concept in statistics and statistical reasoning where the technology really can build some new insights. All along the way, we'll be trying to highlight how these embody the mathematical practices, and we'll always be open for, it says there at the bottom Q&A, but you can, with that chat window, you can pose questions along the way, and there'll be somebody looking there to try to pick those up and relay those to us. At the end, Eric, we'll turn it back over to him, and he'll touch on some other resources that are available to you at the conclusion of the webinar.
So basically, by the end of the webinar, we're hoping that you'll have some understanding of what Tom and I call action consequence lessons. You'll be able to, in an action consequence lesson, the student does take some action on a TNS file and immediately can observe the consequences, what mathematical result happens, and try to figure out what the impact and what are the consequences of that for understanding and learning mathematics. We'll look at some lessons that relate to the Common Core State Standards. We'll think about the standards for math practice as kind of ways that we should be thinking about structuring our interaction with students and our expectations for them to think about and do mathematics in our classrooms. As Tom mentioned, we'll reflect on the kind of unique role that we think technology has in order to help students develop an understanding of mathematics. And then you'll see some of the TI-Nspire documents and activities and teacher notes. And then, of course, we're trying to make sure that you can stay in touch with webinars and conferences.
Great. And so now we've made the transition to the teacher software, and the panels that were formerly available on the right side of your screen, they're still available. You just need to access them using the Event Controls panel in the lower right-hand corner of your screen. So if you hover your cursor over that panel and click the dialog box, that'll bring up the chat window, and then the question mark will bring up the Q&A window. It's all yours, Gail.
Okay, thanks, Eric. So here's the task. Find another pentagon, a non-congruent pentagon, that will have the same area. So Eric is already moving things, but Eric, put it back to the beginning so that we can just figure it a little bit. How would you think about, what would you do to start? Some kids will just start dragging. Some kids will think about, well, what area do I already have? And so kind of get an orientation to the way you think about doing this. So perhaps maybe you're going to make the rectangle longer and skinnier. So you're going to go down 1 and over 2 to the right. And so then we're going to keep that rectangle there. And then we're going to have to say, well, now what have I got? I have a, and I hope you can see that it's on a grid. So the bottom is 1, 2, 3, 4, 5, 6. So it's 12 already. The original area, if you calculated, was 16. I have way too much. Can I bring that peak down? Will that work? How is that going to give me? So now I have 1/2 times 6. That's 3. I'm only to 15. I'm going to be in trouble here, I think. So kids can experiment and move and try all sorts of different ways. Now I have different combinations, and each kind of way that they move and that they think about this, they can calculate the area. And you'll notice, if you think about this, that kids will use a lot of different strategies. Some of them will just aimlessly drag. Some of them will try to use the compensation strategy. Eric, go back to the original one again. And one of the things that's kind of interesting to me is, as long as I've been doing this, it's 4 across the bottom and 3 up, Eric. I've been working with this problem quite a bit. I think it has to go 1, 2 down. The sides have to go 1 down. Yeah. Okay, so there we have our original pentagon. One of the last things that people think about is preserving the rectangular area on the bottom and changing the altitude on the top. So if you take the vertex of the triangle and move it over, there's something really unique that happens here because I've preserved the altitude and the base, and so I have the same area but a clearly different pentagon. You can achieve the same thing if you go down to the bottom and change the base of move that one to the right 1 unit, and then move the other one to the right. Now I have a parallelogram that has exactly the same area. You're going to have some kids wondering whether or not that vertex in the middle of what looks like a straight side, is that really a straight line segment, which is a good opportunity to have some discussion. Mary, can you go to 1.4, please? One of the interesting things that you might have kids experiment with is, if you look at this one, they might take the top left hand of that and move it up 1, and then go to the right hand one and move it down 1. And now our question is, are the 2 areas of those 2 triangles formed by the dotted lines and the sides of the pentagon, are those areas equal? In other words, is there a compensation strategy going on here? And what strategies might you use to figure that out? How are kids going to come to finding out the areas of those 2 little triangles and finding out whether they're equal? We're not going to take the time right now to do this, but that's something for you to think about. So let's look back at the PowerPoint. And one of the really key things here is to have the students share. If you have a TI Navigator, you can put up all their possible solutions and talk about them. If not, you can put these together on a worksheet or have kids display theirs on a document camera. But you want to actually have a conversation about, is that first, the one in the second row in the far left, is that really a pentagon? What about the definitions? Which of these are right? What goes on? Is the one in the 3rd row in the left, is that an okay solution? Is it the same? Will it satisfy our requirements here? So we want to get kids thinking and comparing. The next one, please, Eric. The interesting thing is that this problem comes from the National Assessment of Educational Progress, Grade 8, 2005. There were 2 questions. The first one said, find the area of the pentagon. The second question was the one we just looked at. 48% of the students got it partially correct, which meant probably they could find the area. 2% of the students could answer the second question. Not a very robust response. Next, please. One of the things that we're hoping is if we think about the Common Core State Standards and the way they are approaching area starts in grade 3. It's finished in grade 6. So the basic formulas, the work with polygons, composing, decomposing rectangles, polygons, is done by grade 6. So the kinds of activities that we just looked at with the Pentagon problem is a kind of activity that should be done in grade 6 to help kids come to understand and experience what happens when they compose and decompose rectangles and triangles to try to figure out area. Next, please. So another really important part of the Common Core State Standards are the mathematical practices. These practices are the kind of shaping for what ought to be going on as kids are thinking about how they do the mathematics in your classrooms. So we want them to be making sense of problems and reasoning abstractly and modeling with mathematics. And if we think about this pentagon problem that we just did, we could see that there are ways that these practices come to life. Next one, please, Eric. One of them is the math practices and technology, using appropriate tools strategically. And if you think about what we were just doing, we were varying, exploring consequences, using our tools to explore and deepening understanding, and we were analyzing solutions generated by the technology. So technology has a unique role, particularly in this case, the interactive dynamic technology. Next one, please. And when we look at the pentagon problem, clearly students would be making sense of problems. They're using pictures, they're comparing solutions, they're constructing arguments and critiquing the reasoning of others. They're distinguishing what's right from what isn't. They're explaining and making sense of what their solutions are and helping other people understand. And it's pretty important when you're thinking about area that you look for the structure. You need to have that perpendicular altitude in order to have the height. They're also breaking apart this shape into different kinds of objects, into triangles and rectangles and squares. So the pentagon problem really does help kids think about the mathematical practices and make them come to life. I'm going to turn this over to Tom for the next one.
Okay. So the next scenario we're going to look at is one that would fit in well in the Common Core State Standards in the material and volume. On an earlier slide, I've seen that the polygon area stuff is generally finished up around grade 6 in the Common Core State Standards, but then you move to more general figures, including ones with curved surfaces like circles and cylinders and such. This is also the scenario we're going to look at is also a great one for looking at the notion of a function that's modeling a relationship, in this case a geometric one. Next slide, please. So this is kind of a snapshot of what we're going to see in a second. In fact, won't spend too much time on this. The title is Filling the Urn, but let's go to the live dynamic version so you can really see this at play. So we'll go to the teacher software now. So let me just set up the scenario for you here. On the left, you have a picture of an urn or a vessel that has circular cross sections. And we can fill that urn by using the little clicker at the top. Every time we click the up arrow, we add 1 unit of volume of liquid to the urn. And the graph on the right is depicting the fluid level or the height of the fluid in the vessel as a function of volume. So the more we pour in, the higher up the level goes. We actually you can empty the urn too by clicking on the down arrow, so we can move up and down. So for a particular vessel shape like this, the kinds of questions you could ask of students could be around this coordination of that physical scenario. And the physical scenario in this case is rendered virtually, but it's dynamically linked to this graph, and the graph tells a story. It tells the story of the filling of the urn. And of course, then there's some qualitative questions about the shape of the graph, its slope, and relating that back to the context of the shape of the urns. So here's we can see that the graph here is fairly steep, and yet if we pour in some more fluid and get up kind of above that bend, we start seeing the graph bend down. It's not increasing as quickly. And making sense, reasoning why does that make sense? What I like about this scenario a lot is this is one that kids have almost universal experience with. They've all experienced pouring fluid into some bottle where the neck gets narrower and suddenly it fills up much more quickly. So they know, they have some practical experience, and this is letting them in this virtual environment play with that. What's at a different level though now is one can actually alter the shape of the vessel, and the graph is automatically and dynamically updated. So that raises a whole bunch of different and interesting questions that have to do with shapes of urns and shapes of graphs. For example, one could pose this question: is there a shape that would make that graph on the right perfectly linear? And I'll let you think about that a little bit. And I can't hear you because you're all on mute, but I'm imagining what most of you are thinking. And let me tell you what a few kids will say. Well, they'll actually answer a cone, and you might want to think why they might think a cone would be appropriate. But notice it's something that can be checked out and tried. So Eric here is kind of making a more of a cone shape. Not quite. Let's see. Close, but you can see the part. Wow, that's metaphysically kind of weird what happened there at the top. But but we can see that that's actually concave down. Okay, what we'd really want is a cylindrical shape. And again, that's something then we can check out. But so students can try things out, make conjectures. Students can challenge each other, and behind all this is we want them to be making sense, making reason, justifying their answers. So here's a nice cylinder, and sure enough, there's that nice cylindrical, that nice linear graph. Okay. Just for fun, I'm going to throw out a tougher question for you all to think about. And that would be, what if the picture of the vessel was covered and all you had was a picture of the graph? Could you uniquely recover the picture of the urn just from the graph? In other words, we can see that the urn determines the graph, but is that an inverse relationship? Is the graph determine the urn? And it's actually a fairly subtle question that depends on, you can bring in some interesting concepts from calculus there, like cavalieri congruence that underlies definite integration. I'll go ahead and lift the cat out of the bag here. In this particular case, because these are all, the cross sections are all circles that have a common axis, it is indeed the case that the graph determines the urn. But in more general shapes, if we were allowed to have, for example, a slanted cylinder, we could still get a linear graph even though we had a different urn. Okay, let's go ahead and return to the, unless, I'll invite Gail, though, if she has anything she'd like to add in here.
The only thing I want to add is I think this is a really important one for kids in 8th grade when the Common Core State Standards say they're supposed to be understanding linearity. But they should understand, notice that the height is your vertical axis and you're looking for where the change in the height is constant. Trying to help kids make that connection is really important.
The other thing I think I would add is this is actually a file I've used with a really broad range of students. Students in middle school, 6th grade, as well as calculus students. Of course, my terminology and the vocabulary that I might use with those different groups of students will be different. But this is one that has a wide range of applications. You can start talking about related rates and things like that in calculus with such a, but it works very well for younger students too.
So one of my favorite questions is, how can I do it so it has 2 points of inflection?
Ooh, very nice. think about that shape. So the math practices and the filling the urn, you know, I won't read through these, but you can see there's ample opportunity with a task like this to give students experience with these math practices. And if you all forgive me, I'll jump on a soapbox here. To me, this is the potential for the Common Core state standards to make a difference is around the math practices. We've had a lot of different versions of content standards, but my worry is that those often atomize our curriculum, where people are looking to check off a particular content standard that was addressed each day. The math practices, though, what they invite us to look for are really rich problems, really rich scenarios, and by its very nature, you should be hitting multiple math practices with a rich question or a rich scenario. And so looking for those, I hope we start putting a premium, because those are the ones that are really going to allow us to engage students and give them the opportunity to engage in these math practices. I'll get off the soapbox now, and we can go to the next slide.
So I want to switch to an algebra context and think about sometimes really rich problems can come from very simple situations. And I know you guys have all struggled helping kids understand the difference between expressions and equations. The research literature is pretty clear that this is one of the things that kids have big trouble with. And the Common Core state standards pretty much tell kids that they need to be understanding some of this stuff about equations and expressions in middle school. And so we want to look at a very simple one and called the number line. And if we go right to the TNS file there, basically what I have here is a number line. The domain is from -10 to 10. You can drag the X and notice the output changes. And this is kind of just a simple task. It can be positioned to do lots of things. So the questions that you might ask, or I should actually say, if this were a workshop, I'd be asking you guys for the questions that you would think of. But you can actually ask pretty simple ones. You can say, is the output ever going to be divisible by 8? What would it take in order for that to happen? You can say, is there an input that would make an output of 0? Which can move us towards understanding something about domain, because to get an output of 0, it doesn't actually happen with the domain that I'm restricted to. So it's got to not be an integer that's going to give me an output of 0 if there is one. We can look at that and say, what do I think is going to happen for every 1 unit change in X? What's going to happen to my output? So if I change X by 1, it seems to have gone from 5 to 8. If I go 1 up, it's going to go, I'm beginning to make a conjecture that maybe the output increases by 3. And so my question then is that an accident? Or what about that 3 in the expression? Does that have anything to do with it? Why? Can I justify? How does that relate? And notice that I'm opening up the door to thinking about function, to thinking about rate of change, as well as just thinking about evaluating expressions and looking at the output. Go to page 2.1, please, Eric. And here, I suddenly have switched. I've added an equal sign, and now when I drag, I'm looking at a very different question. My question is no longer what's the output for a given input. The question is there an input that will make that equation, that statement, a true statement? Can I find some value of X that will make the left side have value 11? And there it is. at x equals 5. So now I want to know what's the difference between what I just did with the expression and what I'm doing here. I want to know, maybe, is this the only value of x for which this would be true? Can I find other ones? Can I justify why or why not? So I can play a lot of kinds of different problems, different questions, trying to help kids make sense of the difference between an equation and an expression. Okay, let's go back to the PowerPoint, please. One of the things that we actually are looking at is the math practices in terms of expressions to equations. And again, if you just think about the kinds of open-ended questions that you can ask, we can do what Tom was talking about. We can actually get kids to be thinking and reasoning. We can make these practices, help them come to life and make the mathematics make sense for them. And it's all kind of dependent on the interaction between the student and the prompts that you get them to think about in order to make those mathematical practices come alive. I'm going to turn this back to Tom.
Okay. So before we go into the next example, it'll actually illustrate what we've found helpful to think about two different lenses you can use to think about the role of technology in a math classroom. One of those roles is a tool for just doing the mathematics. It's like a task servant. You have some computation you want performed. You have a graph you would like plotted. You have a spreadsheet you'd like filled out. You'd like some statistics calculated. And these are tasks that might be, because of the sheer amount of data involved or the complexity, is something that you know what you want done mathematically, but you're going to turn that task over to the technology to assist you. That's a role that's very important. We use it in problem solving. It frees us up to strategize what mathematics we want done, and then the technology is dutifully waiting there for us, and it will do our bidding, but we need to tell it what we want done. There is a different role for technology to play. It's not a more or less important role. It's just very different, and that is explicitly using the technology to illustrate concepts and to provide these kinds of exploratory environments where students can play, but play in mathematically meaningful ways, not random play. They can do something purposefully to explore and think about math concepts. Again, both of these things are beneficial, but they're very, very different ways of using technology. Let's see, I think we'll go, so picking up again on something continued, we saw the functions at play and the modeling that goes on with the EARN. We're going to look at a kind of a classic problem here that really lets us look at functions through multiple representations. And by the way, will let us use the technology in both of the roles that we just saw on the previous slide. Next, let's see, are we ready for? Okay. The particular problem we look at will involve algebra and geometry both, and even calculus could be at play. This is the setting. A sailboat has two masts. One's 5 meters tall, the other's 12 meters tall. And the masts are 24 meters apart horizontally. They must be secured to the same location using one length of rigging. So you can see that yellow outline there. The rigging comes from the top of the 12-meter mast to a point, and then from that point to the top of the 5-meter mast. The total amount of that, total length of that yellow polygonal path is what we're trying to minimize. We'd like to use the least amount of that as possible. All right. So in a technology environment, if you've got dynamic geometry, this is a fairly simple diagram that we can make dynamic. So we can actually enact in a virtual environment. We can actually see what different, and in this case, notice we have no measurements there. We're just kind of eyeballing the length of the total length of the rigging there. So what are some approaches that we might use to this problem? Well, if we go to the next page, 1.3 of our document, with a dynamic geometry environment, we can actually investigate this empirically. And that is, we could actually measure the distance from point P to the bases of the two masts, and then calculate the total length of rigging. You can see the rigging from point A to point P and the length of rigging from point P to point B, and those are totaled up there in the upper right corner. And just by experimentation, let's see, Eric's getting it smaller, 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 and no, it's still a little smaller, still a little, oh, now I think it's turning around. So somewhere in that kind of 17 from the base of point of mast A there, somewhere in that vicinity, we've kind of empirically found what looks like a local minimum. Okay. If we go to the next page, we could try to actually model this algebraically. In this case, now we've replaced this kind of numerical value with a literal variable x. Okay, x is standing for the distance from point P to the base of the 12-meter mast. That leaves 24 minus x as the distance between P and the base of the other mast. And then by using the Pythagorean theorem and some algebra, we can come up with what we might think of in calculus our objective function. This is that total distance of rigging from point A to point P to point B. What could we do with that function? Well, if you have calculus, and so for example, here's another role for the technology could play, though we won't illustrate it right here, is if you had a computer algebra system, you could actually have ask your task servant to aid you in taking the derivative, setting it equal to 0, finding the solutions, and then kind of testing those to see if that would work. Eric almost did it, but he doesn't have to. A non-calculus result could be obtained by just taking the objective function and graphing it, and then looking at the graph to find that local minimum. Okay. We're going to look at now another solution that doesn't use algebra or calculus, and this is one that I'm guessing a lot of you, when you saw this context, you might have seen, oh, I know a very elegant solution to this. So we want to use geometry to find the sweet spot that P should be to minimize that rigging. So we've got our original scenario here, and the geometry that we're going to illustrate is just activated by this clicker. We've set up a way to show what's going on here. And what we've got is we've reflected the mast, the 5-meter tall mast has been reflected through the deck of the ship. And we'll notice that with that reflection, that means if you move P to the left a bit, okay, so the distance from P to the reflected point, or reflected top, so where B is reflected down, distance from P to B is the same as the distance from P to that reflected point. Well, clearly, the distance from A to that reflected point is minimized by just going straight to it. And so that really gives us this elegant solution. If we place P at the intersection of just that straight line cutting across the deck, that's giving us the minimized length of rigging. And if you think back, that's approximately where Eric had it when he was empirically playing around. This was around where he saw the minimum. Okay. So there was a case where we had lots of different ways, algebraically, calculus, geometry, lots of ways to approach this problem. All right. Now this is actually a problem that Gail had shared with me, oh gosh, it's been a couple of years ago. And I think one of the most intriguing things was she shared with me what a student came up with. And so we're going to go ahead to the next page, Eric, And a student came up with an entirely different geometric solution. Her solution went something like this, and we'll just illustrate by if we click. Her solution was, well, let's just connect the top of the 12-meter mast to the bottom of the 5-meter mast, and vice versa, connect the top of the 5-meter mast to the bottom of the 12-meter mast. See where those cross. Go straight down from there. So that point D is the crossing point, and this student's conjecture was the right position for P is just directly below that point. Now, in this picture here, P is at that optimal place, and if we just eyeball it, it looks like D's right above it. But is that just an accident? Is that just something that kind of looks right here? But is that truly the case, that you could just connect up the tops and the bottoms of the two masts and just project down and that would give you the same point? It really raised an interesting question that maybe is obvious to some of you, but to me, I had to really scratch my head and think more about that. And what was fascinating to me was it really opened up a whole new problem to think about. So we started with this mast problem, which is a nice problem in context with multiple representations and approaches available. But now I've suddenly got a new problem to think about. And in thinking about this one, let me show you a little illustration that shows you how rich this is. Okay, let's go ahead and click all the way here. This is a picture that shows a 12-meter mast and a 5-meter mast. And this is the student solution, where it just they've crossed the two, the top of one to the bottom of the other. Now, Eric, I'm going to have you put that one back. And I want you to go to the bottom of the smaller mast and move that point down until the other line is horizontal, almost there. Okay. Great. Now, what I'd want to point out to you is these two pictures are our two geometric solutions. The original was the student solution, and if you look at this picture, this looks like the reflected mast solution. Though notice that Eric did not reflect the mast. He actually translated, he slid it down while keeping the tops and bottoms hooked to each other. And in fact, are those things really lined up? Well, if we click on the clicker here to the left, we're going to get an extra line that's parallel to the two masts. And notice that it goes through those 2 points. In fact, more generally, if Eric would grab and slide either mast anywhere he pleases, so he moves that one down. Now he could grab the 12-meter mast if he'd like. The crossing between those two will always lie on a parallel line. Now, I will leave to you, the listeners, to figure out why that's the case. What is the mathematics going on there that would guarantee that all of those intersection points line up in such a nice way? This is the nice thing about a problem that's rich enough, is that sometimes it gives you hidden riches. This was a case where a new problem kind of arose out of a student's unexpected solution that could lead us to some really interesting new places, and places that are actually accessible. This is, I would claim that, you know, students that had the geometry to do the original problem, all of what we've done here is using the same kind of geometry, but going off into a nice general direction. Okay.
So, Tom, I want to point out two things. First of all, what you've just gone through really shows the use of the two uses of technology, where you're actually exploring and deepening some understandings, and you're also using it to move forward in thinking about it. The other thing I want to point out is when I actually did this with my class, when they had the Pythagorean theorem, the sum of the two square roots, and did the algebraic solution. Eric, you can go back maybe to that page. One of the very first pages, yeah. Where they did the graphing. Yeah, that's the one. So they actually, almost everybody in my class, these were seniors at in the pre-service program at Michigan State, and they were math majors. Almost everyone did the setup of D equals, drew the graphs, traced, and found the minimum, and nobody did anything else. They didn't think about whether that minimum was unique. Was it? How did they know they had the solution? And kind of unfortunately, nobody thought about calculus as requiring the fact that they really needed to take the derivative and look for those critical points. So that was kind of interesting to me, but it shows the kind of powers of technology and also how careful we have to be to help kids think through really carefully what they're doing with the technology. But this is a great problem, and it's really interesting and challenges kids from algebra, geometry, all the way through calculus.
I should share, too, I was actually presented this problem to a group of math teacher educators recently. And it was interesting that when we got to this, I really saw the tool use come into play. So when this objective function that we're seeing on screen right now came up, and people started to, for example, try some calculus with it with paper and pencil, a lot of them started reaching for their computer algebra systems because it was really quite messy. The thing is, they knew exactly what they wanted to do. They wanted to take a derivative, set it equal to 0. They were turning to the technology as a task servant to do it. I also have to add one more thing, that in this audience happened to be Mike Shaughnessy, the current president of NCTM. And Mike Shaughnessy is a sailor, and he quite took me to task that this is not the way they rig masts on sailboats. So we may need to tweak our context here a bit. Okay. So these slides here are just kind of reviewing the math problem and, again, highlighting where the mathematical practices come to play. So I won't read through this, but this is, in the red there in bullets, and especially the modeling with mathematics was certainly at play here. Again, the thing I particularly like about this problem is that it shows multiple representations and approaches, but also that kind of dual role of the technology. All right, I think turn it back to Gail.
Yeah, the next one we want to look at is of all the kind of changes that are in the Common Core State Standards, there's a lot of them at the middle school. Probably the most significant at the high school, to me anyway, is the increased demand or suggestion that all students, will come to understand some pretty important statistical concepts. And kind of, I've highlighted two of them here, thinking about all students and thinking about where we really are today in terms of helping all students. We kind of do a lot of data analysis, which is mostly done by 6th grade. The Common Core State Standards are asking us to start moving into inferences in kind of a gentle way. And so we want to look at an example. The agenda at the beginning said confidence levels. We really want to do confidence intervals. Confidence levels are going to be a different approach. So we're going to look at a file here that can help us think through in kind of a gentle way. And so I'm going to have Eric click on the arrow, and it's going to generate a random sample of 62 men and women. And the little blue dots are the men, and I'm going to kind of estimate how many men I have here. I can count them: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. So give or take 1 or 2, I got 28 out of my 62 men. So I'm going to click over because I'm not very good at my arithmetic. I'm going to go to, I'm going to go over to my calculator up here. And I'm going to say 28 out of 62, and I want to get a decimal answer for that. And so I can say, all right, I chose a random sample of 62 people, and 45% approximately were men. So the question that I have is, what does this tell me about the population as a whole? Suppose these were people who came to a coffee shop at a certain period during the day. So if I were to sample them, I got 45% of the 62 that were there were male. What does that tell me about the proportion of males who show up at this coffee shop? So we're going to go to 2.1. And I'm going to say, well, what is if I knew that the proportion was 1/2? So I knew the population that I was looking at had 50% men. So I'm going to draw a sample of 62. And I can look if I hover over just one. If I hover over those, I notice that in one sample I had 48% of my 62 were men. In the other sample I had 61%. So I'm getting a lot of variability in just looking at two different samples that would have been drawn from a population where half of the people are males. So let's keep drawing and see what we get. So I can keep looking, and I'm going to generate here a sampling distribution of the proportion of men, knowing that the population is half male. I always, when I do this with my kids, they're always saying, wait, 0.3 has to catch up. That's kind of what's going on. But you notice that the sampling distribution of population proportions here, or of proportions, go from about 0.34 to about 0.65. And they kind of do center around 0.5. Well, let's try that again, Eric. All right, and so we're going to generate a second set of 100 drawn from a population where we know that half of the people are male. And this time it's about 0.4 to 0.65, still centered around 0.5. So it's kind of different, but not all that much different from the original. So I could continue to do this. And let me just see, that 0.45 that I had my observed sample, looks like it could come from a population where half of the people were male. Let's go to the next page, 3.1. I'm going to look, okay, 0.4. Suppose my population percent was 0.4. I knew that 40% of the population was male. Let's look at a simulated sampling distribution of the proportion of men. Drawing 62, looking at the number of men in each of those. And the question I actually have here is, does my 0.45 look like it fits? And it seems like 45% would be a logical candidate to have occurred if the true population proportion were 0.4. Let's try 0.6. Eric, can you set the P to 0.6? All right, and then let's see what happens this time. So if I continue to generate this sampling distribution of proportions of men, knowing that the population is 0.6, it kind of looks like my 0.45 is a marginal candidate there. If I hover over the points, I can kind of see 0.46, but it's right kind of on the edge. So maybe, maybe not. Let's go to page 4.1. Let's kind of do this systematically. So let's go and set P hat to 0.45. All right, so that was our observed sample proportion. 45% of the sample were male. And I'm looking at 0.5. And a population of 50% male, it looks like that's a yes. So Eric, click a yes. And notice down on the horizontal number line on the bottom, it says this is a possible proportion. The true value could be 50%. I would be likely to get a sample where 45% were men if the truth were 50%. So let's change our 0.5 and let's go make it a little bit bigger. go 0.52. Oh, no, that's not good. Let's back up. Okay, put a yes there. Looks like 0.53. Now, I'm not being exact about this, but that's okay. I said at the beginning that there was a difference between confidence levels and confidence intervals. And right now, all I'm trying to do is to think about the confidence interval. I'm not being real exact. You can come back and attach that exact and get all the p-values and do all that fancy stuff if you want to. But right now, I'm just trying to kind of by inspection say, I'm not going to go much below or above 0.53. Let's go the other direction, Eric. So I'm seeing a lot of yeses. You could be clicking yeses if you want to, but basically all of these true populations look like they might generate a sampling distribution. We want to go the other way. Go down. Yeah, that's the direction. Keep going down. Right. Keep going down. Still looks pretty typical. Still okay. I'm getting on the edge. And kids might, I'm going to say that's the end. That's my last yes is 0.38. So what I actually have now is a set, an interval from 38% to 53%. So I could actually have any of those percentages would be likely to generate a population, a sample, where 45% of them were male. And so I could say I have, in statistical terms, a confidence interval that goes from 38% to 53%. Now you can stop there, but the Common Core State Standards actually ask us to go one little bit further. They want us to talk about margin of error. And so that would be to take that interval 15, divide it into 7.5, and I'd get between 45.5 plus or minus 7.5%. So my interval would be 45% plus or minus a margin of error of 7.5%. So this is kind of a gentle way to get kids to think about what really is a confidence interval for proportions. And again, I'm not going to go through all the math practices, but this kind of engaging in simulation and exploring, thinking about the structure of what's happening are important ways to build the conceptual foundation for coming to understand very subtle and often tough to learn statistical concepts that now we're expecting all kids to know and to be able to do. Tom?
Okay. So in terms of the technology and the role of the teacher, for the teachers to make effective use of the technology, they'll need to understand these affordances that a particular application or software can provide. But the really key part here is providing activities that will allow students to engage in these math practices as well as have opportunities to confront their misconceptions and get feedback. Orchestrating discussions around these kind of discourse-worthy tasks is another, I think, a really emerging pedagogical practice. We were talking about mathematical practices. I think this is a pedagogical practice that I'm finding more and more important, is to be able to orchestrate those discussions so that students really get the mathematics and the engagement in the mathematical practices out of the activity that they need to. Next slide. Black and William, if you're not familiar with them, they are just tremendous thinkers around the use of formative assessment. And they really have laid it online in some really readable terms that the tasks we choose students to engage in, they've got to be justified in what the students are going to be able to learn from engaging in them. And this last bullet here is one I really love. There's only two legitimate reasons to ask a question of a student. It's either for you to be able to probe how they're understanding the mathematics, or the questions intended to push their student thinking, their thinking forward. Next slide. Just a quick look at what a math-inspired lesson looks like. Texas Instruments does have several activities that make use of the technology. Each one has extensive teacher notes that lay out, clearly stated math objectives, and actually include reference to the mathematical practices. Next slide. These are some questions from one of those activities, and what I'd draw your attention to is, at least here, I'm not seeing very much of calculate this or write down the answer. These are asking students for the difference between an expression and equation, to come up with examples, to explain what something means, to explain why. And so those kinds of questions are really trying to elicit some sense-making and reasoning on the part of the student. And I think the next slide. And this is certainly not only implicit but explicit in the Common Core state standards. Is kind of what we might think of as an equity principle, and that is they really are about providing opportunities to help all students learn mathematics. And I hope we've made the case in this webinar that dynamic technology really can be a powerful lever to help us teachers